Hello everyone, this is Prashant Athavale from Triple E Department BMS IT. I want to discuss through this audio lecture about the series resistance and inductance circuit excited by an AC source. Recall from our previous this particular portion has already been discussed in the class. I hope that you all have notes about the same that we have written in the class, and maybe keep that as the reference, and then some of the slides over here also you can refer to, and then try to understand about the concepts. Try to build your own explanations about the simple things over here, and then this is how we want to learn over a period of time. You can see there is a circuit diagram given over here where there is this resistance shown by its symbol as well as an inductor. The resistor is connected in series with the inductor and is being excited by a voltage source of say V of t. Now, and the bottom two graphs that are shown, waveforms that are shown, you can see one is for the pure resistor. So, if the pure resistor is excited by the voltage source, then the resulting current will be in phase with it. You can see that both the voltage and the current will reach their maximum value at the same time, whether it is positive maximum or the negative peak. They will reach their maximum value simultaneously. They will reach their zero values also simultaneously, and they will cross the zero mark and venture into either the positive half or the negative half simultaneously. So it means that the current and voltages are in phase. This is applicable for a pure resistor. But for a pure inductor, the scenario is a little different. You have discussed this in detail in our basic electrical class concerning about pure inductor. So you can refer to that notes. Over there you have written that the current will be lagging the supply voltage exactly by 90 degrees. So this is the whole discussion that we have done. But now it is not a pure resistor which is supplied by the voltage, nor the pure inductor. It is the combination of the two. So the two are connected not in parallel but in series. Sorry, but in series they have been connected in series. They have been connected in series, and what will be the effect of this whole combination. So we'll go to the next slide. This is the question that is now to be posed. So if the circuit contains both the resistor as well as the inductor, what will be the phase relation between the voltage and the current? Not just that, if there is power being consumed, which one will consume, which one will just store and send it back. If power is being consumed, what is the magnitude of the power, and so on. So these are the some of the questions that we will try to answer through our lecture over here. Again, going back to the same resistor and in series with the inductor, you can see there is a phasor diagram shown where VR, VL and VS indicate the voltage across the resistor, voltage across the inductor, and the supply voltage VS, all shown through the phasor diagram. And the current I is the common element through all these three. Therefore, that has been taken as a reference. And first you draw the current, and then in phase with it you write the voltage VR, and then leading that current will be the voltage VL, and the sum of these two, that is VR and VL, will be the voltage supply Vs. Of course, this is not to be scaled over here, just the conceptual representation. Um, so the prominent thing that is to be observed is what is the phase relation between the resulting current I and the supply voltage. So you can see that there is this current and there is this voltage. Current is lagging the voltage by an angle theta, as clearly shown over here. theta is not 0 nor it is 90 degree. It is lying somewhere in between 0 and 90 degree. So this is what we are now going to see in detail further. So let's go to other aspects of the resistance and inductance in series. So if there is resistance only, then what is the opposition to the current? It will be, say, capital R ohms. And if there is only inductance in it, then the opposition to current will be because of the inductive reactance, which I represent as, say, XL ohms. But now you have both resistor as well as inductor, so the current opposition will be something called as an impedance. So the impedance will be given in terms of the given in the units of ohms. So it is the combined effect of resistance and inductive reactance as a whole. There can be 2 3 resistances in series with an inductor. There can be multiple resistors and multiple inductors in series. So net effect, net opposition is this inductive reactance. So you can express in impedance as R plus jXL. I repeat, R plus jXL. R over here represents the resistance and XL is the inductive reactance. The sum of these two is the total impedance. So magnitude of that impedance can be real part square plus the imaginary part square. So real part is R and imaginary part is XL. So you can find out that under root, if you write this thing, then you will get the impedance, magnitude of the impedance. So this is the total opposition to the current. Similarly, you can see that there is this theta. So that theta is nothing but say as shown in diagram, say B, or phasor representation C. So this is the angle between the resulting current and the supply voltage. That angle is related closely to the magnitude of or the relative values of XL and R. So theta can be very easily represented as tan inverse of XL by R. So this is the formula for determining the theta, that is the angle. Going further, we can see that the resistor and the inductor. Before that, once one slide I have included wherein types of resistors are shown. There is a linear resistor and non-linear resistor. There are non-linear resistor like a thermistor. There is a LDR, light dependent resistor, varistor resistor, flexible resistor, and so on. Each of them have innumerable applications in small electronic circuits and hobby projects and so on. So you can search about them and you can know more about it. You can Google them. Similarly, over here, this linear resistors are also there, where fixed is there, variable is there. These are the two categories shown, and some pictures are also shown over here. So I think it is very useful. Maybe you can pay some more attention. And these slides are there on the website. So on the internet you can find all this. So if you recall from the class, I have discussed at length about some of these resistors. See, you can see that there is this metal oxide resistor. It is written as a 3W, right? So this is the wattage, 3 watt resistor it is. So its power rating is given and so on. So variable resistor rheostats are also there. A trimmer is there and so on. Okay, so these are some of the types of resistors. So irrespective of the type of resistor, of course, no, except the non-linear resistor, if it is linear resistor, uh, what is its behavior in the circuit when excited by an AC source? Similarly, I am showing you one more slide wherein the inductors are shown. So a coil, you have discussed in the class, at length about how the inductor is there, right? So its inductance value and its dependence on factors like the number of turns, the length of the core, then the permeability over there, and so on. No, we have discussed so many such things, core material, cross section, and so on. So all that picture collection is given over here, where it is wire bound and ceramic and so on. So this is one more slide which is, I think, interesting. You can search these things over there. I have given even the link also. um, you can see in the next slide about these types of so these are usually, this yellow colored small transformer that you can see is usually seen in the chargers, smartphone chargers and other devices. So you can think of it. So transformers and so on. So on the one more circuit board is also given. So there is place for the processor and various other components over there. Heat sink is also visible. So all this you can see there is a inductor also here. So there are some of the places where you can see inductors being used. Okay. So now, yeah, one more interesting thing is, this is one example of a copper inductor, some very old photograph of an inductor which was used for some communication circuits. So it is able to send, it's part of a circuit, which is used to send and receive messages over 6,400 kilometers. So the inductive reactance, as you know, depends on the frequency, that is 2 pi FL. So since frequency is there, so it can be put in connection with the resistor in such a way that it becomes like a low pass filter or a high pass filter and so on. You can make such circuits through this inductors, not just this one component as a standalone, but in combination with other components. You can definitely tune it to suit your requirements. So when I say that there is this resistor in series with an inductor and it is being supplied by a voltage source, then what are we actually going to do with it? So I said in one of our classes that we are going to analyze a given circuit. Analysis means that circuit components are given and circuit input is given. So we are going to determine what the output of the circuit will be. Output in a general sense, but we are actually determining the current through each of the components, like the resistor and inductor, maybe voltage across each component, like what is voltage across resistor, then what is voltage across inductor, and so on. Then we will determine what is the current flowing. Then we will determine what is the power dissipated by each of the components, if they are dissipating, and maybe we will represent the individual values using the phasor diagrams and so on. So for this analysis, sometimes circuit parameters are given, or sometimes uh, sufficient data will be given to determine maybe the inductance and the resistance only, and so on. So it depends on what is the question that you are actually trying to answer. But in general, you can say that analysis means usually the circuit components are given and excitation is given, that is the voltage source, and you will be asked various other parameters. So it is very much essential that you know the relation between each of these components very well. For example, what is the relation between frequency and inductive reactance? So you know that XL is equal to 2 pi FL. So if you are given the frequency and the inductance, you will be able to definitely determine the inductive reactance. So if you are given inductive reactance and inductance, maybe you will be able to determine the frequency and so on. So interrelation you should very thoroughly you should be knowing. and phasor representation. And one more important thing is ability to operate with the complex numbers. So addition and subtraction, multiplication, division of the complex numbers is very much essential. So if you are somewhere lacking in those area, maybe you should practice well, learn to use a calculator very well. This will help you in easily calculating the values. So over here, the Ohm's law is used to determine the voltage. V is equal to Iz is our Ohm's law, and we will be also determining the power. So you have listed some three powers over here. What are those? Real power is there, reactive power is there, and apparent power is there. So these are some of the parameters that we shall be determining. So in the next slide, you can see here there is a mention of something called as power triangle. So this is just the extension of the impedance triangle that we have seen in previous one of the slide. So this prominently you can see that there is this phase angle theta, and there is this capital P, capital S, and capital Q. So what are each of these things? So P is the real power, or the true power, or the active power. So it is going to be measured in watts, and the formula for this is VI cos theta. Cos theta is nothing but this cosine of the angle. So what is this angle? What is the significance? This is the angle by which the current will be lagging the voltage. So if the current is in phase with the supply voltage, then angle will be 0. I repeat, if the current is in phase with the supply voltage, then angle is 0. If angle is 0, then cosine of that angle is cos of 0 is 1. So in that case, we'll say that power factor is 1. And if it is a pure inductive circuit, so let's suppose if it is a pure inductive circuit, then cosine of angle, what will be the angle? The current will be lagging the supply voltage by exactly 90 degrees. Therefore angle will be 90. The cosine of 90 will be 0. Therefore vi into cos of 90 is vi into 0, which is 0. That means real power or true power is going to be 0. That means the inductor will not consume any power. That's how, this is one more way of saying the same thing. So this is our real power. Similarly, reactive power is also there. It is measured in var. So va is volt ampere, and R is for reactive. So sometimes we write VAR, sometimes we write kilo VAR, that is K VAR. So unit for reactive power is VAR, unit for real power is watt. Now the sum of these two is, of course, vector sum of these two is the apparent power. The formula is also given over there. Formula is given over there as S is equal to under root P square plus Q square. So if you know these formulas and the relation between each of them, then you will be able to determine any one of the value given another other remaining two values. Okay, so this is called as power triangle. So you practice this also. Now, how is this theta dependent on the impedance and the reactance? So, if reactance is very large, obviously theta will be very large. If resistance is comparatively lesser than XL, then theta will be somewhere tending towards 90 degree. In that case, it is inductance is more prominent or more strong in the given circuit. So that will lead to the conclusion that the actual component which is consuming power is resistor, and that is weaker in the circuit, and maybe less power will be consumed. On the same lines, if resistance is more prominent or stronger, then reactive power, sorry, this real power will be larger and reactive power will be smaller. You can imagine such a power triangle where this Q is small and P is longer. So in that case, the theta will be somewhere closer to zero. It may not be exactly zero. It will be exactly zero if it is purely resistive circuit. So if it is closer to zero, then cosine of that zero angle will be the required power factor. So you call cosine of that theta as the power factor. Power, again in red letters we have written that power consumed is because of ohmic resistance only. So inductance is not consuming any power. So this is the power triangle. Um, so continuing with this power factor itself, we can say that it is the cosine of the angle theta. Whenever we are solving these numericals, more discussions, we'll do more discussion about the power factor further. Uh, some text, yeah, and we have also written here that the textbooks, use theta or phi or such other some symbols. So whichever textbook you are following, you feel free to use that nomenclature. Okay. Uh, so what is that theta? Theta is the angle by which the current is leading or lagging the supply voltage. Now the question that should arise into your mind is, it is possible that the current is lagging the supply voltage by say an angle of say 45 degrees. In that case, cosine of 45 will be 1 by root 2, that is 0.707. Now it is also possible that the current could be leading the supply voltage. So then in that case also it will be 0.707, that is cosine of 45. So there is possibility that current is leading by 45 degrees or current is lagging by 45 degrees. In either case, the cosine of the angle will be same. But how do I differentiate that in one case it is leading, the other case is lagging? So, apart from the numerical value of the power factor, there is one more word to be added, that is the word leading or lagging. So that will complete the power factor. If you just say a power factor of 0.707, it doesn't convey full information. It doesn't convey whether the circuit is capacitive in nature or inductive in nature. So you need to you need to add that leading or lagging component over there. Then only it will be a complete representation. So as you already understood, I have taken one example here in the next slide. You can see that if it is say 0.75 lagging, so if you write it as 0.75 lagging, it means that the current is lagging the supply voltage. So 0.75 means you can find out what is the angle. So cos inverse of 0.75 is 41.4 degrees. Okay, so you can put your calculator in degrees mode and you can find the inverse of 0.75, cos inverse of 0.75. You will get to know that the angle is 41 degrees. What does this mean? It means that the phase difference between voltage and current is 41 degrees. Because of the word lagging, you can also say that the circuit is inductive in nature, and hence the angle is as it is 41.4 degree, and also it is lagging. And the other one is this 0.64 leading. So I have taken one more example. So the 0.64 is nothing but cos of theta. Cos theta is 0.64. It means that cos inverse of 0.64 is 50.2 degrees. The 50.2 degree means whether the current is leading or lagging, either case. But it is specifically been mentioned that the current is leading. So what does this mean? It means that the circuit is capacitive in nature. So, henceforth, whenever you are being asked to determine the power factor of a circuit, you need to be careful about the determination process. But at the end, you should also indicate whether the current is leading or lagging by suffixing this, information as to leading or lagging. Sometimes you can just write a lead or lag. That is also sufficient. Continuing on this discussion, let's take one example over here. This is an example wherein a circuit description is given, but the circuit constants are not being specified. Circuit constants are the resistance and the inductance. You can see that resistance as well as inductance values are to be found through this particular description. So you can read the description of the example. As you have maybe as you have understood, it mean what it says is that there is a circuit which is having a resistor and inductor in series with each other, and it is being supplied by a 10-volt AC source. Now the 10-volt source can have two frequencies in this particular example. Once maybe it is 50 hertz, and maybe sometimes it is 75 hertz. So when it is 50 hertz, it is giving up a current of around 700 milliamperes. So this is the resulting current when the 10 volt is 50 hertz supply. And the same supply, when it is having a frequency of 75 hertz, it is producing a current of 500 milliamperes. Now question is, if this is the case, what are the values of resistance and inductance in the circuit? So you have to find the value of resistance and inductance, which is totally impeding the voltage such that a current of 700 milliampere flows in one case and 500 milliampere flows in another case. So this is achieved by just following the simple Ohm's law. Ohm's law, we know it is V is equal to I into Z. So I am taking the magnitude of Z, which is V is equal to I into magnitude of Z. What is magnitude of Z? Previous one of the slide you have seen that it is the real part square plus the imaginary part square. So it is V is equal to I into under root R square plus XL square. So I just written X. I should have written it as XL square. So here you know voltage and the current. So there are two possible cases. So first case is when the current is 700 milliamperes and the frequency being 50 hertz. Second case is current being 500 milliamperes and the frequency being 75 hertz. So you can substitute the values. Say 10 is equal to, in either case the voltage is still 10 volts only, that is not changing. So 10 is equal to 700 into under root R square. R, why it is R square? Because R value is not known. That is what we want to determine now. Therefore it is written as R square only, plus XL is nothing but 2 pi FL. Now you can look at the next part of the equation. I have directly written that as 98,696. So how is that possible? So it is 2, then pi, and frequency is 50. So 2 pi into 50 is 314.159. So if you square that number, you will get something like 98,696. So this is the expression. Now 10 is equal to 700 milli into this part. Therefore you can rearrange the term. You can bring 700 milli on the other side. Then you can take the square root, and if you rearrange the term, you will get the equation 1. I have marked the equation 1 as R square plus 98,696 L square equal to 204.08. So this is our expression 1. On the same lines, you can look at case 2, that is 10 is equal to 500 milli into the resistance. So what is astonishing over here is that the value of XL. So XL value depends on the frequency. So for 50 hertz, whatever is the inductance, the inductive reactance will increase if it is 75 hertz. So that is very much obvious. You can write down some hypothetical example and then calculate for value of inductance for 50 hertz as well as for 75 hertz. So as the value of inductance increases, obviously the magnitude of the impedance increases. And as per Ohm's law, I is equal to V by magnitude of Z. So for the first case, magnitude of the impedance is less, therefore current is 700 ampere milliamperes. And for the second case, the magnitude of impedance has increased and therefore the current is also reduced. So this is how, and you can make changes, and you will get the expression 2. So solving the equation 1 and 2, you can get the values of resistance and the inductance. Um, so this is our example 1. So this is a little different type of example, so I have specifically chosen this one. Let's look at the next example. Here, the idea is to determine the power factor of a given circuit. So no other details have been asked, so you don't have to worry about it. If required, you can definitely find it. But the question is, in this particular case, what is the power factor? So to determine power factor, all that I require is the resistance and the magnitude of the impedance, or inductive reactance and the resistance. So either of using either of this, you can definitely find it. So let's read the description of the numerical example. So here it's said that 1.5 kilo ohm resistor is connected in series with a 2.2 kilo ohm inductive reactance. So there is no mention of inductance and we don't require over here also. So we just require the value of XL and value of R. Both of them unit is ohms only. And this is being connected across an 18 volt source. So what is the question? Question is to determine the power factor. You can look at this impedance. It is written as 1500 plus J 2200. You can see, recall from our previous slide that theta is equal to theta theta is equal to tan inverse of XL by R. So theta is tan inverse of 2200 by 1500, and you can determine the theta as 55.71 degrees. So the cosine of this angle is 0.5633. Now, as I mentioned previously, if you just say that the angle is 55 degrees, there is possibility that the current could be leading. Current can lead by 55 degrees, definitely. Current can also lag by 55 degrees. In either case, the cosine of that 55 degrees will be 0.56 only. But if you mention along with this lagging, then the answer will be complete. So that's what is mentioned. I have mentioned that information in green. So it is lagging by certain angle. So here you can see that 56 0.5633. It means like 56% of the power is getting converted into useful power. 56% of the available power. If you recall the expression for power is equal to Vi cos theta or Vi cos phi. So cos phi or cos theta, any one symbol you can use. So if you rearrange the term, you will get from this equation. I repeat, P is equal to Vi cos theta. You can write cos theta as P by Vi. So in the numerator you have P, in the denominator you have Vi. What is the unit for P? It is watts. What is the unit in the denominator? It is V into I. V into I is product of voltage and current, which is the apparent power. You can recall that power triangle, there is capital S written, so that is the apparent power. So One more definition for power factor is the ratio of real power to apparent power. So that way also you can interpret this. So the ratio of apparent real power to apparent power is only 56%. So 56 percent means remaining 44% of the power is not being utilized by the given circuit. So that's how it is. And if you keenly look into the description of the example, there is the voltage being given, that is 18 volt. That is not used anywhere in this particular expression. So we don't require that. If you follow this method, if you moving to the next example here, I have taken a 1.2 kilo ohm resistor in series with a 15 millihenry coil, and it is being connected across a 10 kilohertz AC source. So all that has been asked is what is the magnitude of the total impedance. So magnitude of the impedance depends on the value of the resistance as well as the inductive reactance. And inductive reactance in turn depends on the inductance and the frequency of the supply. So here the frequency of supply is 10,000 hertz or 10 kilohertz. So all that information, if you were to substitute into this, you will see that the magnitude of the impedance given by this total circuit, that is resistor in series with the 15 millihenry coil, is around 1500 ohms. So this is the way you can take few other examples and substitute into this formula and you can find. So if you recall some 2 3 examples that we have solved now, each numerical is trying to determine maybe only the power factor or only the magnitude of the impedance and so on. Let's try to combine these and try to find one more example. I think it should have an example 4. So this is a 1 kilo ohm resistor is in series with a 100 millihenry coil, and this is being supplied by a 5 volt source, 500 hertz AC source. So you will have to determine the magnitude of the impedance, then determine the current and also the power factor. So you can see that the total impedance depends on R square, R as well as XL. So separately we have found out the XL. XL is 2 pi F into L. This is 6.28. That is nothing but 2 into pi is directly written as 6.28. Frequency is 500 and the inductance is 100 millihenry. So if you find the product of all this, it is going to be 314.159 ohms, and resistance is 1000 ohms. Therefore, if you put all this information into that formula, you will get to know that the impedance, total impedance is 1.048 kilo ohms. So what is the current? Now to determine the current, I have used this formula here, Ohm's law. I is equal to V by Z total, which is 5 plus J0. Now what is the meaning of this J0? It means that 5 volt it is, 5 at an angle 0 you can write, or 5 at an 5 plus J0 you can write. So I written it that way, and in the denominator I have written the R plus J XL. So R is 1000 and XL is 314.159. So these two, when if you put it in the polar form, it will actually look like 5 at an angle 0 and 1048 at an angle 17.44. So you can divide the two numbers by dividing the magnitude separately and subtracting the angle. So actually the current will be now 4.77 milliamperes. Okay, 4.77 milliampere at an angle of minus 17.44 degrees. So what does this mean? It means that magnitude of the current is 4.77 milliampere, and with respect to a voltage source of 5 at an angle 0, the current is lagging by 17 degrees. Okay, so this information is put in terms of the power factor. So power factor here I have used phi instead of theta. So it just be get acquainted with either type of usage. So power factor is cos phi equal to cosine of that angle equal to 0.954. So don't forget to write this word, that is lagging. Okay, so this was our one more example, and we need to next find the voltage across the resistor and voltage across the inductor. So voltage across resistor is nothing but current into resistance. That is our voltage. That is the Ohm's law. So 4.77 milliampere into 1 kilo ohm is 4.77 volt. So pay attention to this small case m and k. So milli stands for 10 raised to minus 3. Similarly, k stands for 10 raised to 3. So don't forget to substitute their values by while calculating, either in calculator or in by hand calculation. So don't forget to use those milli and micro and such values. And voltage across the inductor is 1.499. So this so if you were to just add the two numbers, that is 4.77 plus 1.499, if you were to add, the sum will be around 6.3, right? So the it is but where is the supply is only 5 volts, so you don't have 6.3 volts, so sum of these two. So you will have to add them as shown there, check. Okay, under root vr square plus vl square. So if you add, you will get the value of the vs as around 5. Okay, so that's how the whole exercise is. So I hope that you have understood the calculation of these parameters, voltage, inductance, and power delivered, and so on. So in the next 1 hour or the other class, we'll continue with determining the real power, the apparent power, and the reactive power. Okay. If there are any queries, you feel free to discuss in the class group, and I shall try to answer it as quickly as possible. Thank you.